Alright guys, so hopefully you watched my little video on Young's double slit experiment with a laser. Okay, and I just wanted to write down the data for you. What we did was we had our laser, okay, and the distance from the double slits to the screen was 2.0 meters, okay. We had our wavelength of the laser beam. It's a helium neon laser. Is 636 nanometers. And what I found was 4 delta x's on the screen was equal to 9.4 minus 6.4 centimeters. Okay, that's in centimeters. So let's just solve that right away. I'm just going to put in brackets that was in centimeters. So you get 4 delta x's was equal to 3 centimeters. Okay, so therefore delta x would equal 0.75 centimeters. That's 75 millimeters, or if you like, 7.5 times 10 to the negative 3 meters. Okay, everything has to be in standard units. Okay, so this 636 nanometers would be 6.36 times 10 to the negative 7. Actually, you know what? Well, nano is 10 to the negative 9, so I'm going to write not normal scientific notation, but I'll just write 636 times 10 to the negative 9 meters. That's how I entered in my calculator. All right, so now, like our goal was to determine D. What is D? In other words, how close together were those two slits? They are so close together. In fact, I'm going to include on this page, I'll add it later, but like a picture of those slits. They're so close together that my camera can't resolve the distance between them. Okay, I can't even tell that there are two slits there. So, you know, I'll try to take a better picture later, but yeah, they're so close together that it's difficult to see that there are two slits. You can tell that some of the other ones, you can see in the video that some of the other ones were two slits, but there's a very small distance, right? And so it's a very useful thing what we're doing here. We're using the laser to measure the distance between two things that are very close together, okay? And that is one of the applications of this technology, okay, of light interference of light waves, okay? Anyway, so D, what is D? So now we know the formula. The formula goes like this: delta x equals L lambda over D. Okay, now that's one of the formulas that we developed when we did double two-point source interference. Okay, and so I'm going to solve this for D. We'll just cross multiply these two things. We'll just switch places, right? So D will equal L lambda over delta x. Okay, and now all I have to do is, it's such an easy experiment, right? All I have to do is plug in the numbers. Okay, and we'll see what I get. So when I plug in my values into my equation here, sorry, I just got to pull up my calculator. All right, so I get 2 meters times 636 times 10 to the negative 9, and then divided by 7.5 exponent 3 negative. All right, and I get 1.7. I'm going to round it to 2 significant digits. 1.7. I really can't have more precision than that because my experiment, I did the measurements very coarsely, okay? So I get 1.7 times 10 to the negative 4. I'm doing that right? 1, 2, 3, 4, yes. 10 to the negative 4 meters. So that's not even a millimeter. That is less than 0.2 of a millimeter. So they're very, very close together, okay? So that is equal to 0.17 millimeters, okay? Or, if you like, about 170 microns. So that's a very small distance, okay? And it's kind of cool how that works. Like, so one time on a final exam, like just to give you an idea of how you could use this, one time on a final exam I said, okay, could you design an experiment to measure the width of a hair, like a human hair? Okay, and what kind of tools would you use for that? Well, the best way to do it is not using a microscope. Okay, microscopes are okay, and you could definitely use a microscope to measure something like that. But there's another way to do it. Okay, and in fact, you can use this laser, and all you have to do is you poke a hole in a sheet of paper, and then what you do is you put the hair across the hole. Then that'll make two slits, okay, with the hair in the middle. Then you shine the laser onto the two slits, so you get a double slit pattern, and then you find D. And D is the distance between the slit centers. Now, it's going to be slightly wider than the hair because there's some gap in the because of the width of the slit. But you know what? You can factor that out. I'll show you when we do single slit interference. There's a way we can actually factor that out and get exactly the width of a hair. Now you might think, well, a microscope would be simpler. That's true for a hair. But what if you're measuring something so small that the microscope can't see it? Okay, microscope magnification maximum for an optical microscope is 10,000 times. Okay, so what if you're looking at something that is so small, like on the scale of a micron or even smaller, that it's going to be very difficult to measure sort of the distance between those things? Well, you can use this kind of experiment for that. Okay, and then we'll get this interference pattern, and using the interference, we can measure very small distances. Okay, so anyway, there you go. So that was the distance between the two things. Now, I think the accepted value on that apparatus that I have is 0.156 millimeters, something like that. It's one typesetting point. You know how you have points on a font, right? And a 2-point font would be really small. Imagine a 1-point font. 1-point font is incredibly small. Well, what are the distance between the points on a 1-point font? It's about that number. So it's quite small. And that's how they make that plastic card. They make it using a typesetting machine, and they set the points to a very small value in order to produce those slits. So anyway, there you go, double slit experiment. We did it with the laser, way easier than Thomas Young. It really shows dramatically, how light behaves like a wave. And so there you go, that's the experiment. So I told you it was a short experiment today, and it is. In the homework, if you could please, okay, I'm just going to show you where we are. We are now here in the homework, okay? I think next week we've done enough this week, but I think next week, it's mostly been notes this week, I hope you realize. Remember that I just want to point something out to you. We did this last week, okay? So really all we've done this week is these two sections of homework here that I'll just we've done this one and that one, and now we're doing this one, okay? Not really a lot there, guys. I'm just going to tell you, I'm probably going to throw in another worksheet on this, okay, on the double slit interference, and I will post that shortly, okay? The questions, super easy. You're just using the formula. That's all you have to do. Some of them are a little unusual, so I think you'll need my help with a couple of questions, so please send me your questions. Other than that, we're good. Next week, we're going to look at other kinds of interference, okay? And the other kinds of interference are really interesting. First, there's single slit interference. That's not so interesting by itself. It's sort of like double slit. But then thin film interference is really cool, okay? Like, why are a butterfly's wings really beautiful? Well, it's not because of pigmentation. It's because of interference. Why do soap bubbles have swirls of color? That's called thin film interference. It's the same thing. And the interesting thing about thin film interference is definitely they would have seen examples of that in Isaac Newton's time, but didn't know it was interference. So anyway, that's kind of an interesting thing. And then there's this Newton's ring apparatus. I will show you that too. Air wedges, thin film interference. That's really one topic, one lesson. So we just have 2 lessons. We'll do them both next week. And then maybe at the end of next week, we'll have a test. And then we have quantum physics left in the course, and that will finish the course for us. We'll get it done. It's just about a week. It's about 5 lessons, so we will get it done before the end of the course, and that's it. Okay, so yeah, that's it for today, guys. Have a good day, and we'll talk to you soon.